Another idea I want to talk about is critical points, but this really encompasses several things. So I want to mention a couple of ideas. So that is, what can you learn from the first derivative? And also, what can you learn from the second derivative? So let's talk about things you can learn from the first derivative. What can you learn from the first derivative? What does the first derivative tell you? Well, it tells you a little bit about critical points, yes. So oftentimes when we talk about critical points, it says derivative is 0. Right? F prime equals 0. That's usually what we think of as a critical point. But generically, if I tell you, oh, the derivative here is 7. It tells me slope, which tells me behavior of the curve. Yeah. In particular, increasing, decreasing. So when do I know, when am I increasing? When it's, what is positive? The slope is positive. When am I decreasing? When I'm negative. All right, now second derivative, given what we said about increasing, decreasing, what is the second derivative going to tell us? Concave up, concave down. Okay, when are we concave up? Second derivative is positive. When are we concave down? Second derivative is negative. What does it mean to be concave up? Well, that's telling us how the curve is bending. So generally speaking, when I think concave up, the curve is bending up. When we're concave down, the curve is bending down. So we can start to sort of identify things. We can sketch ourselves a graph. And we say, all right, suppose we have a function and this is y equals f of x. And I can ask various things. When I'm asking for things such as critical points, what am I looking for in this graph? So critical points, where do I tend to think of critical points as being? Now be careful. I drew here y equals f of x. I could have sketched something similar and said y equals f prime of x. Can you recognize the difference? So if I'm in this graph and I say I'm looking for critical points, where am I looking? If I'm thinking of it as a f of x. They tend to be maxes or mins. So I say, oh, critical point. Critical point. Now, another thing that could happen is if your derivative is undefined. All right, and then we can tell, oh, this is a max, this is a min, this is a max. If I come here and I say, where are my critical points? Where am I looking? I'm looking for the zeros. So for the derivative, I'd say, critical point, critical point, critical point. Yes? Now, this was a max. We could just read it off. Come down here. This critical point, max or a min? How can you tell? Well, that's a critical point, right? But what kind of critical point is it? Is it a max or a min? Okay, so based on behavior, what kind of behavior? What's behavior to the left?
Decreasing.
This is f prime. So f prime is positive. That means we are increasing. So it means we're coming up. What's behavior to the right? Where f prime is negative, decreasing means we're going down. So what kind of critical point is this? Up, down, so this is a max. How about this one? Down, down. So what is it? Neither. So critical points look different depending upon whether you're looking at the function or the derivative. What about an inflection point? Are there inflection points up here? They're a little bit hard to plot, but I claim there's roughly, here's an inflection point, here's an inflection point. What's happening at those points? Changes in concavity. How do you find inflection points if you're not looking at the function, you're looking at the derivative? What are you looking for? Okay, so concavity is basically doing something similar to the first derivative. So right here in this stretch, are we concave up or concave down? Concave up. Why do you say concave up? Positive slope. So this is the derivative. So the slope being positive tells us the second derivative is positive here. What's happening here? Because why? So negative, or decreasing the first derivative means that our second derivative is negative. So our second derivative is negative down to here. Then what happens to our concavity? It becomes positive again because we're increasing over to here. And then what happens? Become negative again. So we actually have 3 inflection points. So depending upon whether you're looking at the function or whether you're looking at the derivative, you might say, oh, this is a critical point, or you might say, oh, it's an inflection point. So make sure you know what function you're looking at if you see a picture problem, and think about how do you represent those pictures. Think about what's going on. So you have some tests. Now we talked about finding these in terms of the picture. We have the first derivative test is basically saying look on either side. So if you have a critical point, if your first derivative goes positive, negative, then that tells us we are a local max. What happens if we're negative and then positive? Local min. And then if we're negative, negative or positive, positive, then it's neither. Second derivative test. If the second derivative is positive at a critical point, what are we? So what kind of critical point are we? If we're concave up at a critical point, what kind of critical point do you have? Local minimum. Because concave up says we are coming up from the tangent line. So we have that type of behavior. Second derivative is negative. What are we? Local max. We are bending down from the tangent line. Second derivative is 0 at a critical point. What are we? We don't know. Ah! Okay. So that's our various rules. How do you find critical points? You can find them graphically. Make sure you know, are you looking at the function? Are you looking at the derivative? You can find them algebraically. Take the derivative, set it equal to 0. And yeah, that's a lot more about critical points than we probably needed to say, but any questions? All right. Cool. Let's move on to, and if we have time, we'll come back and revisit some of these examples. Optimization. So I like to think of optimization as one of the big reasons we have calculus. Because this is the place we can go and say, hey, we can make you money. And people are like, I like the sound of what you're saying. Tell us more. So what's happening with optimization is it's about getting the most that you can, given the constraints that are available. And the world is full of constraints. There's a lot of things where we can't be like, oh, let's just pour infinite resources in, because we have finite resources. So we say, okay, given that we have finite resources, how do we make the most of what we have? So the way we solve optimization problems is really, it's all about going back and finding the critical points and finding the max and mins. So the real key step to optimization is you want to set up a function of one variable. And what we're trying to do then is once we have that down to a function of one variable, then we're going to say, okay, what's the right choice? So we do this by finding the critical points. And then we are going to check. Now, keep in mind, critical points includes boundary. So it can happen that you might say, well, the best thing to do is to go to an extreme case, so a boundary case. So optimization is really most of the work, and the hardest part is saying, how do I translate words into a function? And this is a skill that's very useful to have, because you're learning all these great tools to solve mathematical problems, but the world doesn't normally present itself in formulas, right? So you have to say, how can I translate what I'm seeing in the world into formulas so I can use these tools? So let's see if we can't set up the function. Maybe we won't work it all the way through. So here we go. A silo will be built consisting of a cylinder with a hemisphere on top. In other words, it will look like a silo looks, right? And so you have your cylinder, and then you have your hemisphere. And we can draw in some cows or something. So here we have a cow. Not relevant to the problem, but might as well throw in some artistic liberties. You have a budget of $180 for the materials. The size costs a suspicious number, 1 over pi dollars per square foot. The hemisphere costs, again, a suspicious number, 4 over pi dollars for square foot. Determine dimensions that will maximize the volume. Now, we start thinking about, well, what do we have? Well, we have cylinders and hemispheres. Now, don't worry about the formulas. I'll give you the volumes as needed. How do you find a volume for a hemisphere? Well, hemisphere means what? Half a sphere. So the volume of a hemisphere is 1/2 of a sphere. A sphere is 4/3 pi r cubed. Now, a cylinder, do you know that one? It's the base, and the base of a cylinder is a circle times height. So pi r squared h. So our volume is, if we multiply this together, 2/3 pi r cubed plus pi r squared h. Now, that's the volume. What are we trying to maximize? We're trying to maximize volume. Okay, so we're like, woohoo! So now our goal is maximize. Now, are we ready to start taking derivatives? And why not? Yeah, it's not in one variable, right? There's r's and there's h's. So right now you're like, well, just build it 100 miles tall, right? We haven't put anything that says you can't. So there's constraints. So it's how do you get the constraints involved? Well, what's constraining us? Cost. We have a budget. $180. Okay, so we have to think about what are the costs. Okay, so, well, we have 180, that's our budget, equals we have 1 over pi, then we have to do our side, and then we have 4 over pi, and that's for the top. Okay, so which one do you want to do first? Side. All right, seems reasonable. Now, if you think about a cylinder, it looks an awful lot like a circle that you've moved and just copied up and down, because it's a circle that you've copied up and down. So let's think about what's happening down here. If I'm looking for this length, what is that length? In other words, your circumference. What's the formula for circumference? 2 pi r. So you have a circumference of 2 pi r, and then you just copy up and down h, so then the area is 2 pi r times h. Now for the sphere, it's a little bit less well known, but the area of a sphere, turns out it's 4 pi r squared, but we don't have a whole sphere, we have half a sphere. So it's 1/2 of 4 pi r squared. So what we end up with is we need 180 is equal to, the pi's cancel there, so that's 2rh, 4 pi, oops, no, that 4 doesn't cancel with anything. The pi's cancel, 2 divides into 4, so that's the 2, so plus 8r squared. So we have 180 equals 2rh plus 8r squared. Then what happens? Solve for h. You could try to solve for r, but there's 2 r's, and there's only 1 h, so make it easy on yourself. 180 minus 8r squared is 2rh. So 180 minus 8r squared divided by 2r equals h. Well, you can also write this as 90 over r minus 4r. And now we update our volume. So our volume is really 2/3 pi r cubed plus pi r squared times 90 over r minus 4r. And now, are we ready to take derivatives? Yes. We got it down to one variable. We're ready to go. And so from here, we've translated into a math problem where we have our tools. So from here, it's take a derivative, find your critical points, and work with that. So now that I've used up all my space here, there was one other idea I did want to mention that's related to optimization, which is really about finding max and mins. So the other thing about finding max and mins is, what if we're in this situation where we want to do the following: find an absolute max and absolute min. What do you do there? Sorry, what? Well, you do have to have, you have a function which is continuous, and then you have an interval, a less than or equal to x less than or equal to b. So you do have points, yes. So what do? Do you remember how this one goes? Good. All right. Now, the way I like to remember this, and this, you have the right approach, is I like to say, channel your inner clause. This is the right season for it. And so you just think, we're making a list and checking it twice, gonna find out which points are nice. So your list, always throw in the endpoints, and then throw in where your derivative equals 0, or the derivative is undefined. Okay, so there's your list. Set the derivative equals to 0, check if it's ever undefined, add in the endpoints. Now, if your derivative is 0 outside of a and b, you ignore it. Once you've made your list, Now plug all of these into the function, whichever values you come up with. So this is a list of x values. So that's what you found in your list. And then you're going to plug your x values in, and lo and behold, you're going to come out and you're going to get some outputs. Well, what do you do with your outputs? So the biggest output you get, what is that? That's your absolute max. Smallest output? Absolute min. So if you do have a problem that says, hey, find the absolute max or find the absolute min, you're like, okay, I'm going to go make a list. Going to check the endpoints, check to see where the derivative is 0 or undefined, plug all them back into f, and whichever one's the largest, that's the max. Whichever one's the smallest, that's the min. All right, so again, it's an optimization thing. It's about finding the max or finding the min. All right. So any questions about optimization or finding absolute max, absolute min type questions? All right. Cool. Well, in that case, let's talk about our next topic. Another useful idea, antiderivatives. Now, of course, antiderivatives here are not like, oh man, we are strongly against derivatives. Arr! No, it just says, look, I want to do the opposite of a derivative. And in other words, I want to say, hey, what's the function there where I came from? So, how do we go about it? What are the properties? Well, a couple of basic things to remember. Antiderivatives are not unique. There is a plus c lurking somewhere. So keep that in mind. If you are asked to solve for an antiderivative, and it's a long answer problem, and you forget the plus c, you'll lose a point. And we don't want to lose any points. So make sure you put that plus c in. Now the big punchline is basically, everything about antiderivatives comes from derivatives. So we have these long list of properties. So one very nice thing that we have is that antiderivatives are linear. So what does linear help us do? Do you remember what that tells us? That means you can break it up. So integral of a f of x plus b g of x dx, that's a integral f of x plus b integral g of x. So linear is the part that says, hey, we can pull things apart. We can take big problems and turn them into small problems, which is very useful for us to do. We have a collection of basic functions. And there's 8 that we want you to know. By the time you hit Calc 2, there's 10, but 8 for right now, that's good enough. And you're going to use these for many semesters to come. You might say, oh, I don't know, Steve, this is going to be my last calculus class. Well, even if it's your last calculus class, but you're going to be an engineer, you're going to keep using them. So these are sort of our go-to. And the big spoiler for Calc 2, and I'll go ahead and give you advanced spoilers. We're not going to really add much to this list. Calc 2 is not going to be like, oh, we're going to come up with lots of new exotic functions and find their antiderivatives. Calc 2 is more like, how do we get to these? It's about manipulation. And so be very careful. And when it comes to getting to them, there's 2 big tools that we use. One is algebra. Be open. If you see algebraic things to do, like maybe you can expand or you can break things up. If like you have a lot of stuff on top, you saw this, for instance, on the 3rd exam. You said, oh, what if I have something like integral of x squared plus x cosine of x over x. What do you do? Yeah, you just say, look, I'll do algebra. It's like x squared over x, which is x, plus cosine of x. You're like, cool. You just algebra'd it. You're like, yeah, I did algebra. Pow! You know? So a lot of what you have is algebra tools. So be open to algebra. The other thing to be wary of, and it's probably the most useful thing when it comes to doing antiderivatives, is substitution. It's your go-to tool. After knowing your basic antiderivatives, in other words, after knowing these 8 antiderivatives that you see up here, substitution is your biggest friend. So make sure you know how substitution works. Make sure to know how to carry it out. In other words, if you see an expression, you might have to think, well, how do you find the substitution? Sometimes they'll just say, here it is. We will tell you the substitution, but you have to carry it out. Sometimes they won't be that generous. And if they're not, say, look, I know how to find substitutions. This isn't my first exam. You can either look on the inside and say, is there a function inside a function? If there is, that's a substitution. Or you say, hey, do I see something that looks like a derivative? Because if you see something that looks like a derivative, then you say, well, what's the antiderivative of that piece? And then that could be your substitution. So those are the two things you're looking for, something on the inside or something that looks like a derivative. And when you put them together, then it's heaven. That's what you want. And when you're making a substitution, just remember, update everything. We're going to say this again in a few minutes on a different slide, but make sure you update everything. Because it's very easy to forget to say, I forgot to update this part. Uh-oh, trouble. Now, this is a good point to mention motion, because motion is a fun problem. We oftentimes use that as nice problems and word problem type things. And you might say, well, suppose I look at position versus velocity versus acceleration. How do these relate? So how does one get from position to velocity? Take a derivative. How do you get from velocity to acceleration? Take a derivative. I might say, how do you get from position to acceleration? Take 2 derivatives, right? Well, what if you want to go the other direction? What if I have acceleration and I want to get to velocity? What do you do? Yeah, you integrate. Integrate is just another way of saying take an antiderivative. Now, when you integrate, you get a plus c. How do you solve for plus c? You have initial conditions. If you have velocity, how do you get to position? You integrate. So make sure you know how to move back and forth. So if they say, I have information about position, tell me something about acceleration. You say, okay, great, I can do that. They say, hey, I'm telling you something about acceleration, maybe a little pieces of information, some initial conditions, tell me something about position. So keep in mind that you want to be able to go both ways. All right. Well, any questions about antiderivatives, by the way? Hopefully, since we just tested on it, it's still fresh in your mind. You're like, yes. All right. In passing, we won't spend much time on this, but we know it's coming, so we should mention it, of course. Differential equations. Now, differential equations are very similar to the idea of like finding an antiderivative. And because that's a very simple case of a differential equation. So that's your y prime equals f of x. What's a differential equation? An equation, you see an equal sign with a derivative involved. But you may have something more complicated than that, where there's not just a single y prime term, maybe there's also y terms floating around. in which case we have to solve it. Now, the only kind of differential equation that we can do is one that's separable. So, if you do see a differential equation, in other words, you see a formula with an equal sign, a derivative is involved, and you see other stuff with y, that's the differential equation, then you know it's going to be separable. Because you know it's coming, and you know it's separable, you know the strategy. What is it? Step 1, separate. Step 2, integrate. Step 3, uncomplicate. And I can already see that I misspelled the word separable, so that's why people are like, did you not know how to spell separable, Steve? I'm sorry. Separable. All right. Now I know why everyone was looking at me funny. Any questions about separable differential equations? We can do one really quick. We might have enough time. Should we try one? Because there's one here. All right. Let's see how we do. Okay, so given that y prime minus xy to the fourth equals x, and y of 0 equals 1, find y of x. Okay, we suspect this is a separable differential equation, because that's what the whole paragraph above it says. On the test, it might not be so blatantly obvious. My guess is, roughly speaking, it will probably be in about chronological order. It may or may not be, so be careful. But again, if you see a y prime and you see other stuff with y, that's your clues. So what do we need to start doing? Separating. Now, can we separate right away? It's not looking great. What are some things we can do? Well, ideally, you want to get, like y prime equals something with x, and then something with y. That's the goal. That's the goal. So I'm going to move this stuff, which doesn't have a y prime, over. So I have y prime equals x plus xy to the fourth. Now, I want to factor it, so I have stuff with x and stuff with y. Does this factor into something that looks like stuff with x and stuff with y? Well, yeah, it's x times 1 plus y to the fourth. Okay. So, we're almost there. Now we go into our separate phase. So we see this dx. We're going to move that across. We see this 1 plus y to the fourth. We're going to move that across. And when we do that, we get y over 1 plus y to the fourth dy is x dx. Okay, great. Now what? We integrate, right? We've separated. You know you've successfully separated if stuff with y, stuff with x. Right? Only y is on one side, only x is on the other side. Okay. Let's just do the right-hand side, because that looks so tempting. What's the integral of x dx? Half x squared. Good. And we'll throw the c on that side. Okay, what's the integral of y over 1 plus y to the fourth? Yeah, I was thinking the same thing. Now the problem is the plus sign is in the bad place. It's a plus sign downstairs. Pluses downstairs are bad. Pluses upstairs are great. Because that goes up. Pluses upstairs, we can break things apart. That's linear. How do you handle pluses downstairs? Well, we're going to do a lot of that in Calc too. But we start thinking about substitutions. Is there a good substitution for us? Y squared. Wow, I was going to start with 1 plus y to the fourth. Is 1 plus y to the fourth going to be a good substitution? Why would 1 plus y to the fourth not be a good substitution? Because you don't have a y to the third upstairs. So then someone said, hey, how about y squared? Why would y squared be a good substitution? We love arctangent? That's a good philosophy to have. I agree. Who doesn't like arctangent? Yeah. So there is one case where there's a plus downstairs in our list of antiderivatives. 1 over 1 plus x squared. So we're like, oh, this could be setting us up for an arctangent. So du is 2y dy. So we can then divide by the 2. So a half du is y dy. So if we do this, then this integral here would become y dy is 1/2 du. 1 over 1 plus y to the 4th becomes 1 over 1 plus u squared. Because y to the 4th is y squared squared. This is a case where essentially what we were looking for is this part right here was our derivative, was a nice derivative of something. Right? You either look for something on the inside or look for something which has a nice antiderivative. And the y dy has a nice antiderivative. It's y squared up to a constant. So that was like, oh. So go with a y squared substitution. Okay, antiderivative of 1 over 1 plus u squared? 1/2 arctangent of u. I'm not going to worry about the plus c because I already have a plus c here. Now, do I need to do anything else to this? Yeah. So I started with y's. I need to end with y's because these are indefinite integrals. So 1/2 arctangent y squared. Now, I claim we can do the following. I'll do it right here, and then you can be like, "Arr!" But I claim this is the same as saying arctangent of y squared equals x squared plus c. Why is this true? What just happened? Took out the 1/2, but wait, there wasn't a 1/2 in front of the c. But c is a constant. Constants are like sponges. You can absorb halves and you can spew out halves, you know. So constants are very good at absorbing and as needed. Okay, now, what's our last step? We've separated, we've integrated our last step. Uncomplicate, which means we need to solve for c and y. Which one do you want to do first? Yeah, let's try c. It looks like we may be able to do it. Okay, y of 0 equals 1. In this case, what is x, what is y? So x is 0, y is 1. Do we know what arctangent of 1 is? What? Pi over 4, yes! Nice! So we're like, hey, that says c is pi over 4. Okay, so we're almost there. So we have arctangent of y squared equals x squared plus pi over 4. We're not quite there. We need to start freeing the y. So what's our first thing to free the y? Take the tangent of both sides. Tangent and arctangent undo each other. So y squared equals tangent of x squared plus pi over 4. And now, how do we get the y out of the square? Square root. Now, when we do a square root, we have plus or minus. Do we need the plus or do we need the minus? And how do we know? Do we need the plus or the minus? And how do we know? We don't know? Are you sure? I think there's a way we can figure it out. The plus! Why do we need the plus? Oh, I have a spasm in my finger. Sorry about that. Oh, wait. Because we need y of 0 to be a positive number. That's why. Oh, okay. Cool. All right. There we go. Okay, so differential equation. We're ready for it. All right. A few more things we should talk about. We have a few minutes left. So the next thing to talk about is definite integrals. there's not much to add here other than I'll say the definite integral, we're integrating from A to B. And so we're looking for a total of something. Sometimes we think of it as total area. And that's oftentimes how people think of integrals is area. But integrals are actually more. They're really just saying we want the totals of things. Be open to a few things. Be open to geometry. Sometimes we use circles. When should you be suspicious of there being a circle involved in your answer? Yeah, if you see the square root of something minus something, right? If you see this kind of a setup, you're like, oh, it's A to B. That looks very circlish. Circlish? I don't know. All right, so but that's when you should suspect circles. Look for odd functions. Odd functions can be useful. Remember orientation. If you swap the order, throw a negative in. Don't forget that. That's important. And we can do Riemann sums. I can't remember. Are Riemann sums still on our list of things that might show up? I don't remember. But if not, just remember Riemann sums are just use rectangles. That's all that we need. Now, a quick comment here about definite integrals. Substitution is a great tool for definite integrals. When you do use substitution, what do you need to update? Yeah, update everything, including the bounds. Now, how do you update bounds? Right, if you have the integral of, 2x e to the x squared from minus 1 to plus 1. Oh, that's too cheeky. Minus 1 to 2. What do you get? Well, u equals x squared. So what will our new bounds be? 1 to 4. How did you get 1 and 4? You plug it in. X, because when we write this integral, there's a hidden x equals that we don't write down, but they're still there. So like, oh, these are x bounds, update to u bounds. So make sure you're updating your bounds. It's always better to update your bounds, and then you always are going forward, and you never have to go back. All right, so this becomes e to the u du. And last idea I want to talk about. And this one we should definitely mention. What do you think is the last idea? What's something we haven't talked about yet, but somehow is still very fundamental? Know your fundamental theorems of calculus. Now, one of them we use so often is the one where, say, oh, if I have a definite integral, I find an antiderivative and evaluate. So when we're talking about fundamental theorems, it's almost always the derivative one. So this is the case. This is the one that we don't ever say out loud. So this is the fundamental theorem of calculus, but the way we often use it in practice is suppose you have a derivative of an integral, let's say h of x to g of x of f of t dt. Last thing for the day. What does this become? F of g of x times g prime of x. This is the fundamental theorem of calculus plus chain rule. Is there anything else? F of h of x, h prime of x. So if you remember this part, then you can handle any fundamental theorem of calculus question that we throw at you. And when you see the word fundamental, you know it's going to be fun. And you know how much your instructors enjoy fun problems. So make sure you're ready for these kinds of questions as well.